in 10 minutes, I'll just demonstrate what kind of task that spaCy could do as similar to NLTK. 15 minutes. Okay, first 15 minutes on that. Apart from the primary jobs, what are the primary jobs is your tokenization, followed by the token cleaning. Apart from the primary task, it is having some, I can say, some special task in which NLTK does not offer, which is parts of speech tagging and named entity recognition. In fact, this bit is outdated to the modern day context of transformer model. We are living in the transformer model. It is a bit old because it's part of primary job of the spaCy is for the data preparation, not for modeling. Okay, it's just we can utilize this as a bonus application or bonus task. So this is not the primary role of spaCy. So those days when it was introduced, that time there is no such development that happened, particularly in the transformer-based architecture. Most of the sequence model was done based on LSTM-based. At that time, these were introduced. So it's a bit outdated. Even you can see the kind of results what we get. We'll get an exploration on this and we'll move on. And then I'm going to introduce another interesting data preparation, TF-IDF vectorization. Sometimes people try to use this in two variation. But this is TF-IDF is more standard representation. Earlier, this become popular. Count vectorizer. Count vectorizer. I'll tell you what is the drawback of the count vectorizer, why people shift to TF-IDF vectorization. This is another popular data preparation other than one-hot encoding, which is the dictionary approach. We generally don't use it. And moreover, this representation is very popular for so primarily we are working on the text data, isn't it? So you're focusing only on the content, not on the word order. Whether it could be a recommendation system. It's very popular in the recommendation system. And even classification. I wanted to classify the content, the news articles. So I can say this is text classification. Any text classifications. Having said that, you can even extend this representation. Okay, you can extend this representation even for feed forward model sentiment classification. So to design a feed forward model sentiment classification, you need to have the input representation. There you can represent your each document in the form of a content. But already I mentioned about what is the limitations. Okay, we don't follow that, even though still it works to 70 to 80% efficiency, but we don't do that. So we especially go for sequence modeling for sentiment analysis. So these are the these kind of application. Definitely, if the word order is not so important, content-based applications, you can very well use this representation. So when it comes to sequence modeling, starting from RNN, navigating to LSTM, GRU till transformer. These kind of models, okay, the state of the art representation is word embeddings. Okay, to appreciate and understand the word embedding, there is one separate notebook I have, separate exercise I have prepared for that. We are going to see that in the lab too. Okay, so and we are going to appreciate it. What is the scope of this word embedding? So there are different research team has developed packages. They develop based on different logic, different set of features. That is where it differs. Most of the contribution came from the Google. Okay, Google has contributed, Facebook has contributed. So these were the two dominant contributors for this word embeddings. So that there are different tools comes through different resources. So we have to import those libraries and can use those things. So the state of the art transformer model today we are using in the large language model, which uses the word embedding, okay, along with positional encoding, which makes that as a very special and unique. So we'll be definitely landing this when we introduce transformer model. Okay, this is the first half of today's session we are going to talk. Okay, definitely it will go till maybe 8:30 or 8:40. So the second half I'm going to introduce the sequence modeling. So what are the different approaches in the sequence modeling? So the whole applications we are going to broadly divide it into three major categories. Okay, so the different approaches, sequence modeling approach. So don't be very concerned with whether it is RNN or LSTM or GRU or transformer. So that is why I'm using a very generic term called sequence modeling. Otherwise, your mind will focus on that specific architecture. So initially, I want you to understand how to formulate the business problem. Once you understood the business problem, how to formulate the business problem, obviously, we are going to use the state-of-the-art technique. State-of-the-art means which is more viable in a commercial product. So we'll be going with transformer based. There's no doubt. So for the initial level discussion, focus on the application, the kind of application. Don't worry whether I'm using LSTM or GRU or transformer or even RNN. So towards after understanding the different major applications and how we can categorize the business problem in sequence modeling. Okay, and then gently I'll introduce RNN mathematics. So I'll try to make it as simple as possible. Even we'll reinforce the idea with the help of one simple numerical toy data. So whenever I say about toy data, it's called as a contrived data set. CONTRIVED, contrived data set. So that you can understand the mathematics with a small toy data. Then if you navigate to the real data set, you can understand what's happening under the hood. So you'll understand the math. And of course, I would like to demonstrate with the numerical sequence. Gradually, I will take it to the word sequence. Okay, so you will understand the challenge when you go with the numerical sequence to the word sequence. When it's something like I'm going to predict the next day temperature like 38 degrees, 37 degrees, 35 degrees, 36.5 degrees, 38 degrees. So daily temperature. Again, based on the previous sequence, okay, my sequence model need to predict the next temperature in the order. Like our language model, our focus is, see, the course content talks about language models. Okay, even though I will briefly talk about the numerical sequence to appreciate it, what are the changes when you are extend this idea towards word order? What are the changes that happen? Primarily, the representation of the data itself, there is a change. Because in the word order, everything we try to represent as x of t x of t plus 1 different time step. Okay, next time step, next time step, next time step. So to the context of numerical data, we use the notation time step. Okay. To the context of word order, first sample, second sample, or first token, second token, third token, likewise we use. But general notation is T, okay, which can be extended. This notation can be extended for numerical sequence as well as the word sequence. So here the number representation itself, basically it's a scalar representation. But when you try to represent a token, okay, a single token, we used to represent as a vector. That representation itself is different. Since your input representation changes, okay, the subsequent the weight matrix dimension also changes. So to start the understanding with ease, okay, to ease the understanding, I start with a simple representation, a numerical sequence, what's happening in the numerical sequence. Then slowly I will, because by the time you will understand what is word embedding, how to represent the tokens. Okay, in the next session, I can easily navigate how do you represent the word tokens in the RNN sequence and how the model updates the weights at which are all the junctions it update the weights, what are all the weights involved, crucial weights involved, and how it works. Also, gradually we'll end up with the limitations and challenges and how those limitations and challenges are overcome by subsequent developments. So this is how we navigate. So to continue with, you can take your lab one exercise and we shall continue from there. So there are two data I have shared with you. Okay, not necessarily you should use that small paragraph. Even you can take, I told you to take a larger document, read that file. There are two documents, right? One is a deep learning, one paragraph about the deep learning, another is about the software sports data paragraph. So the first step in spaCy is you have to define your data as a spaCy object. Okay, that is the first step. Whereas in NLTK, that you don't need to do that directly. Once you loaded the data, we have kept the data in the text variable text. So text is a variable. We have loaded the data text. Directly, you can do the process, whatever the process you are intended to do. But here, so this is the spaCy for the English language. There is a pipeline. There are different language it supports. Whichever the language you work accordingly, you have to use those pipelines. So this is the for the English language I have loaded, and my data is read and stored in a variable called text, isn't it? Whereas in the NLTK, directly you can start applying methods, NLTK methods or functions you can apply on your data. Whether you wanted to do the word tokenization or sentence tokenizations or comma punctuations removal, white space removal, comma punctuations removal, and English stoppers removal and stuff like that. Word counts. So once you clean the data, you can go with the word count and try to understand what is the content of the data in terms of term frequency. Word count and the term frequency are both as representing the same meaning. So what I do, so I'm defining my spaCy object here after loading the pipeline. And whatever the raw data, that raw data, which is my raw text is available in text, I have to typecast that as a spaCy object. Once you typecast this as a spaCy object, thereafter you should use this as your data. That is what my text. So throughout NLTK, we have used text. Okay, but here throughout spaCy, I should use text underscore doc underscore object. This is your naming convention. You can keep it any. So by default, okay, if you map any variable on this spaCy object, mapping in the sense like a list comprehension mapping, like generally how do you map in a for loop for defining a variable in this object, right? When you map, by default, this guy is going to return the word tokenization results. Suppose if you wanted to get sentence wise result based on the full stop, There we have used a separate method, okay, the separate method in NLTK. But all you need to do is, by default, this object itself return the word tokenization. The moment you map any variable here, look at this. I'm mapping a variable called token for token in this object, and I'm extracting the text using the method called dot text. Okay, this dot text is the method. It is a method. It is a keyword. Please understand. Don't get confused. This text with this text. Okay, here this text is the keyword. Okay, this is the keyword or method. Okay, whereas this text is a user defined variable in which we have loaded the data. So dot text. But however, if you wanted to extract the sentences, okay, additionally, what you need to do in this spaCy object, you have to include dot sense. So you have to be very specific about, okay, this time you are supposed to return sentence wise. You have to return the data whenever it's being invoked by the local variable dot text method. So what you need to do, dot sense. So the two way I'm invoking the raw data. First, we are extracting all the word tokens, and here we are extracting the sentence tokenization. The only difference is we are incorporating this as a direct method itself. There we are using a different by importing different library like word underscore tokenize, sent underscore tokenize. So there we are using it like a function, but here we are using it like a method. So the moment I run this, you can see how it extracts the individual tokens. Okay, of course, it's a very raw token. It's extracting full stop separately, comma separately, apostrophe, backslash n, all those things. Same way, if you do the list comprehension, okay, the only difference is you have to introduce dot sets. Now, sentence wise, it is extracting every time it is extracting one sentence. So the way of invocation is different, but otherwise the application is same. Okay. So you know how to extract word wise and as well as a sentence wise in both NLTK as well as a spaCy. The next step is how to remove the English stop words, because the different package when people develop, right, it's developed in a different time frame. Definitely the technology advancement happens. So relatively spaCy is more modern when compared to NLTK, as pointed correctly said by Balaji during the last session. He mentioned a very good example. Okay, the analog watch and smart watch kind of. So what people have, they have included few more English stop words in a spaCy when compared to your NLTK. A more refined English stop words they have included. So if you look at in NLTK, there were around 178 or 79 something English stop words, whereas in spaCy the standard English stop words were around it's almost one and a half time, more than one and a half time, 326 English stop words. So randomly, if you are very curious and randomly you print any first five or any because we cannot list all. If you want to list everything, you can list out and see. So randomly, I wanted to visualize a few stop words between 100 to 150 or even 100 to 120. Okay, you can print any random range, you can print and see what are the things it is taken as English stop words, whether elsewhere, else part, and so on. But remember, yeah, in modern day, NLTK is not much used because see your TensorFlow framework and PyTorch framework, they have very sophisticated APIs. Those APIs by default they have internal data cleaning process, the word token cleaning process. So in modern day context, definitely Nobody is going to use NLTK or spaCy step-by-step process. This is just to understand the logic behind how these data cleaning is working.
Okay, sir.
See, for example, even in TF-IDF vectorization, whenever I load this TF-IDF vectorization, see from where I have imported this, I think I have imported this TF-IDF. This TF-IDF vectorizer is even part of sklearn library. Even sklearn library has very sophisticated data cleaning operations, built-in data cleaning operations. And moving forward, we'll be using the word embedding layer, which is part of your TensorFlow Keras layer. It has much improvised version. PyTorch has its own improvised API for the built-in data cleaning process. So as we move on, I will tell how these layers are, what kind of just you can control everything with the hyperparameter. While defining those libraries, when you call those libraries, okay, what are all the things you want to do? Some applications we don't want to filter the English stop words. Certain applications I need to filter the English stop words, isn't it? So for language model, obviously I should not filter the English stop words, because without English stop words, there is meaningless. Sentences are meaningless. The connecting words, which makes the grammar, it makes the tense, whether it's a present tense or past tense. I need to understand the complete beauty of the language is being expressed by the connecting words. So for language model, we never filter the English stop words. But for content filtering, for content-based decision-making process, obviously I need to, because these English stop words are redundant. That's why we are removing it. So everything you can control with defining the hyperparameter. Say, for example, here I'm defining, quickly let me show you and we'll move back. Look at this. When I define TF-IDF vectorizer here, there I say whether I wanted to filter out English stop words or not. If you specify this hyperparameter, it will clean the English stop words. If you don't specify, it will keep it. So you can easily control the process just by playing with your hyperparameters, defining how do you define those here. So what I do, I'm putting a condition, okay, whichever. So our current text, our raw paragraph, which is being typecasted as a spaCy object, I'm posing 3 conditions. Okay, one by one condition. If you wanted to see the result, also you can see. But I have posed 3 conditions by connecting with AND logic. Okay, all 3 conditions satisfies. So it's not part of your stop words, first condition. So this is okay. This method will take care of the moment you say token dot is underscore stop is a method. Okay, just I wanted to show you that method. What are all the stop words that method is it's working with? Those methods is working with 326 stop words. It is going to check whether your paragraph or your token is part of this stop words. Not because it's a negating condition, so it's not part of this English stop words. Also, it is not part of full stop, comma, punctuations, white spaces. So all 3 conditions I pose. If you do only English stop words, still I have some noises in the form of full stop, comma, punctuations. So all 3 conditions I put together, and we are going to filter out only the clean tokens. So it is going to completely purely extract only the content about the data set, removing the English stop words. So all the token which is not part of the subset of the English stop words, or see, for example, if I don't, let me remove this condition. I have removed this condition, one of the condition. Let me run this. Can you see it's not filtering full stop, comma, right? It's not filtering it. So I have to include that condition also. So all in one go, I can do it. Otherwise, step by step process also you can do that. It's your wish. So the next thing is what we are interested to get the word count. There we used a different FREQ underscore DIST function. We have imported frequency distribution function. But over here we have a different method called different library called counter. From collections import counter. This counter is a very generic. It's not part of spaCy, which comes as a generic open library. So I use that counter to count the word frequency, count of each words, unique words, and I print the top 5 most common 5. Sorry, we have not updated, right? So it's including because we have not removed this comma, full stop, and all. Now we have removed the comma, full stops and white spaces also. Learning, data, technology, deep learn. Okay, so there is no English top words comes in the top list. In the same manner, any content, including any large volume, you can check and quickly by just understanding the top high frequent terms. Sometimes see these terminologies are same. Sometimes I say tokens, okay, terms, words, all are meaning the same. We are talking about a particular token or a word or terms, all are meaning the same meaning. So additionally, we have two other important aspects as a bonus application in spaCy, parts of speech tagging and named entity recognition. So while defining different applications, okay, I will tell you what kind of design will you can do similar applications when you design with more sophisticated LSTM or transformer based modules. Okay, with this kind of application comes under what type of design. So I will highlight. So what this is going to do for each and every token, including, it depends whether you wanted to, of course, since it is a parts of speech, I should not remove the English stop words. Maybe you can remove comma, full stop, punctuations, marks, and all. Okay, you can do the filtering in such a way that punctuations and space. Okay, you can remove this English stop words. You can clean the tokens. Those clean tokens, if you pass on to this, and it is going to tell that whether it is a noun or a verb or singular or plural, or it's an adjective or adverb. So every token it is going to define. First of all, it is displaying the token, followed by what is the tag. Tag means the label. So for each and every thing, for example, noun is represented as N, capital N. Like a conjunction, whether it's a conjunction or it is an adverb. A verb is shortly represented as VB. It's tagged as capital VB. So that is what the tag. And we are explaining the tag, explaining the sense whether it is going to communicate whether it is a singular or mass. And so before explaining the things, it is also saying that whether it is a what parts of speech it is, whether it's a noun or it's adjective or a conjunction or it is a verb. So there are three things. In fact, it's a four. The original token. Okay, what is the label attached? It is explaining what is this, and it is giving additional information whether it is a singular or additional context it is giving. Okay, additional context about that particular tag. It's very outdated. You just have a quick check on this kind of application, how to build using our sequence modeling approach. Okay, I will tell as we move on. Similarly, another interesting application is what named entity recognition. just with one method you can invoke the thing. See, for example, to incorporate a named entity, what method I'm using here. So this is our spaCy object, the raw data which is mapped on the spaCy object. Just you call this ENTS. Okay. So for ENT in your spaCy object.ENTS, it is going to return named entity. So what are the typical thing? Your original text it prints. Okay, ent.text, if you say your original text, it is being printed. Here for the sample text I have given here. So the sample text it is printing as it is. And the start of the character and end of the character. So for each one, for example, in this given input, it is trying to identify the name, geographical location, or the organization name. So it's trying to understand, okay, Sundar Pichai is the name. What is the starting index and the ending index? So 0th index and where it ends. 0, 1, 2, 3, 4, 5, 6 is blank space, 7, 8, 9, 10, 11, 12. So the upper limit in Python always it's 13 is not inclusive. It goes up to 12, index number 12. Next, recognizing the organization name alphabet starting index, and it goes up to 30th index. It is saying the label. So the label is printed, isn't it? The label is printed. ORG. Earlier in parts of speech we have different labeling convention. Here we have a different labeling. This is the person, organization, and country name. It is explaining. It's explaining the label. So more detailed explanation about it. What kind of company it is, or it is a geographical location means it is trying to say that it's a city or it is whether it's an urban or it's a rural kind of stuff. It all depend upon already predefined text it is being trained. As I told you, it's a bit outdated. Even if you try to give some recent examples and all, it could not recognize. Okay. To show that, I have given some Indian companies. Most of these data, these guys are trained with US based data sets. Okay, most of the examples they have taken the company organization, the Bay Area companies, or the big tech companies and all. Okay, I have given another example like Tiger Analytics. Everyone you are aware of. It's doing a mistake. You can understand. Okay, what it's saying that Tiger Analytics is being tagged as a person because mostly US data you could see some names like a Tiger Woods and all. The person first name starts with a tiger, so it's wrongly recognizing Tiger Analytics. It's a person. So of course, if you wanted to rebuild the model and all, we have to give more examples and you have to tag and label. And definitely, if you fine tune the algorithm, your model can even recognize Indian company names and Indian cities names and stuff like that. Of course, Bangalore is correctly identified as a city. John is identified. So one of the information is wrong. So it's not up to date. Okay, you cannot use it for commercial day-to-day application, but you can appreciate it. What are all the capabilities of spaCy those days? Because around the 2010 and all, it's a big thing at that time. Okay, at that time we have not, we don't have the sophisticated transformer-based sequence models. Around 2010, between 2010 to 2014, at that time, it's a very big thing. Okay, now it looks like so silly for us, but it's an inspiration for those people to improvise these models based on better sequence modeling. So let us wrap up this NLTK and spaCy stuff. Moving forward, we are not going to use it anyhow. Okay, just you get an exposure. Sometimes you imagine a situation that you are going to build your custom preprocessing. You don't want to use a standard. See, there are certain customization you are going to do it for your product. You are building a product. Definitely, your team, your data scientist team will be building all these data cleaning from the scratch. Okay, maybe that in that kind of situation, when you build some modules or API from the scratch, you can use some certain kind of a customization. Like fine grained selection of the words I told you. Okay, like that, some kind of a customization, definitely if you know how to do it from the scratch, at that time it will be very helpful. For the application scientists, of course, we don't do this. Okay. For R&D team, of course, it could be very much useful when you build something, a new product from the scratch. Okay, now we'll move on our discussion towards the next representation called as TF-IDF vectorization. In fact, the TF-IDF vectorization, it came out as a limitation of the count vectorizer. Okay, so before we see TF-IDF vectorizer, let us talk about count vectorizer. So to appreciate this idea, I have taken this fashion store data set. It has 500 products. So mostly fashion products. It includes, even though it's a say fashion products, it includes some like a wildcraft kind of store, I guess. Okay, it has some mountaineering wear and many sports wear, track shorts and stuff like that. For includes men, women, even it includes some product for the kids also, baby products also. So it has each and every product, it has the descriptions. We are going to process those descriptions. At the end of the day, I need to understand from the content of the token, I need to understand whether it is a men's trouser, whether this is a woman's salwar kameez, or it is a mountaineering gear, or it is like sports wear, whatever it is. It's a kids wear. So that's the objective of it. Maybe you can extend this idea once you understand the content. Maybe you can use this idea for the recommendation system. Okay, taking it to the application, I have used a small recommendation system for it. The recommendation system works on the simple idea, content-based similarity, right? How do you represent your word order in terms of the numerical representation? And you're trying to find the similarity between the numerical representation of one document with respect to another document. Document in the sense, the word the description of the products. So the underlying idea works here is the distance. So if I wanted to apply the distance, first of all, I need to represent a document in the numerical form, isn't it? So first we'll see about the count vectorizer. Even this sklearn, this feature extraction, it has a component called count vectorizer, but it's outdated. That's what I'm not explicitly using it. In which we have much refined representation for it. First step is across all the corpus, it is going to filter out English stop words, obviously, and the unique tokens. So those unique tokens in language models we used to call, in NLP or language models, we used to call that as vocab. Okay, vocab. Let us assume that I have vocabulary size is 5,000. Okay, which includes all the products. Okay, one of the column vocabulary is like a cotton, trouser, sleeve, salwar. Okay, I have a cap, shirt, linen, and so on. Okay, now I have one of the product description is there. Okay, product description for product one. So that product is about some cotton shirt. Assume it's about a cotton shirt. In the entire description, the cotton token appeared 4 times. Okay, and the shirt token appeared 2 times. There is no salwar kameez. There is no trouser token. There's no count for the cap. This goes on up to 5,000 columns. Okay, and this is what the count representation. Count, simple word count, just like how we displayed the count of each token in the previous cell, right? Using counter function or NLTK FREQ underscore DAST distribution. So each and every, this count is called as term frequency. Please make a note of it. It is called as a term frequency. The frequency of occurrence of each token, that is called as the term frequency. What is the term? This is the term. Each and every token is called as a term. What people have done, okay, they have little bit refined this. Sometimes here all the tokens are given with equal weightage. All the tokens are treated equally. What this TF-IDF vectorization concept has introduced, don't treat all the tokens equal. Give some weighting factor. So how that weighting factor has arrived? There is a concept called inverse document frequency they have introduced. Let's try to understand what is about inverse document frequency. This IDF score is being calculated for each and every vocabulary. Please understand. The IDF factor is being calculated for each and every vocabulary. Here we have 5000 vocabulary, means each vocabulary, each token, this inverse document frequency is computed. The formula goes like this. Log base 2 in the denominator. What is my total corpus? Corpus in the sense your training data. 500, right? 500. From the 500 records, you have generated 5000 vocabulary, right? Unique tokens. So in the denominator, it's 500. Okay, denominator is 500. 500 is about how many documents you have taken. The numerator, this one vary for each and every token. For example, let us assume there is a token which is a common for all 500. But we don't have any such token which is common for all 500. Let us assume a different example. Okay, here we have a mix of shirts, women's wear, men's wear, kids wear, and sports wear, trekking wear, shoes, mountaineering wear, even skiing. Okay, for skiing accessories also available as part of this 500. So completely it's a heterogeneous. Okay. Sometimes when you work with a homogeneous records, like all electronic products, all kitchen gadgets or baking products, there are certain tokens. Definitely they are unique, which is going to describe the content. But sometimes they may be redundant. What do you mean by redundant? Say, for example, let us assume all are related to only cloth. Okay, it's about, let us exclude other accessories. Okay, and there is one of the token called cloth. Almost in every description, we come across there is a token called cloth. Assume cloth. So this cloth is made up of so and so, or this cloth is made up of, or some whether it is a cloth, or you just assume any token which is being described in almost that particular token is being, at least it come at least one time. Even it appears one time, it is being counted. Suppose if there is a token which appears in all 500, that count I'm going to put in the numerator. Now what happens? Numerator also 500, denominator also 500. This yields log of 1. What is log of 1? 0. That means you have a token and the count of that token is appearing in every document. It becomes redundant. Why should I include that? Because that token is not going to distinguish my document in any way. So we are going to consider that as a redundant. Say, for example, for the first product, cloth appears one time. For the second product, 2 times it is being used. And 1 time, 3 times, 1 time. Minimum 1 time it appears. So I don't consider this count as one of the representation for this data. Obviously, it is going to scale this with 0. This becomes 0 because it's redundant. So basically, the less frequent token will be highly weighted. Okay, less frequent in the sense I'm not talking about in terms of the magnitude of this number. Please understand. I'm talking frequency occurrence across all the 500 records. That frequency I'm talking about. So instead of 500 record, there is another token which appears around the 490 records. Only 10 records it is not appearing. 490 records it is appearing. Relatively, that token also will be weighted less because almost except 10 records, almost the remaining records it is. So when you put for log base 2 490 by 49 by 50, if you calculate, this will yield something very close to a small number, 0.02 or something like that. You can use calculator and check it out. Definitely will be a small number. On the other hand, if you have only, there are some only, say for example, there is out of the whole 500 records, there are 25 products where linen material out of 500. Okay, so this linen token will be highly weighted. What is the IDF score for this linen token? Log base 2, 25 in the numerator, denominator 500. Definitely, if you calculate, the score will come some weighting value somewhere around 0.76 or 0.78. You can cross check and calculate it. So these tokens are significant or less significant. Okay, from the statistical perspective, if you look at whether this token is highly significant or less significant, that weighting factor also your TF-IDF vectorizer is going to provide. So ultimately, so the structure of your numerical representation of the document goes like this. Document 1, document 2, document 3, document 4, just for an example. Okay, you have token 1, token 2, token 3, token 4, token 5. That is assumed. So how the entries looks like, the entry look like this. 0, 1 time, 0, 2 times, 0. 2 times, 3 times, 0, 0, 0. 0, 0, 4 times, 2 times, 0. 0, 0, 4 times. So from the count itself, we can be able to say that, for example, the document 4, it has the token 4 and token 5. Document 3 has a high frequency occurrence of token 3 and token 4 and stuff like that. Along with this, okay, along with this, let us assume, okay, almost there is no token which is appearing in all. So additionally, we are going to have this IDF factor. IDF, what is IDF factor for T1? What is IDF factor for T2? IDF factor for T4? How do we calculate what is the IDF factor for T1? Log base 2, 1 by 4, am I right? Because it is appearing in one document. But here I'm assuming my total records is 4 documents. So it is appearing in only one document. What is IDF score for T2? Second token, log base 2. For the 2 description appearing, so 2 by 4, right? So again, for token 3, log base 2, 1 by 4. For this one, log base 2, 3 by 4. So out of all the tokens, I think T4 will get the highest magnitude because it is appearing in 3 documents. So for T5, log base 2, 1 by 4. So all these scores are scaled with this. Okay, these IDF value, whatever these values, it will be scaled with each and every record. So log base 2.25, you just calculate and multiply everywhere for T1. Similarly, for T2 counts, for the T2 counts, you should scale each and every value with this value, log of 0.25, log of 0.25, multiply with log of 1. Obviously, this is 0. And similarly, this one will be multiplied by this. This will be multiplied with this. The entire last column should be multiplied by this. So now you understood the representation of TF-IDF representation, right? So basically, it's going to have some numerical representation. Now the job is easy for you. Okay, you have something like 0.15, 0.25, 0, 0, 0.3. Another record is something like a 0, 0, 0.23, 0.5, 0, 0, 0, 0, 0.25, like this. Now I can easily compute distance calculations. So one more record, let me take 0.25, 0.200, 0.4. So 1, 2, 3, 4. If I ask, suppose you are a customer surfing e-commerce, you are looking at this product, right? What are the similar products is going to suggest? This is a similar product for product 1. Obviously product 4, right? Look at the distance. Either you can use Euclidean distance, Manhattan distance, or cosine distance. It computes the distance. 0.15 minus 0.25 the whole square, 0.25 minus 0.2 the whole square, plus 0 minus 0, plus 0 minus 0, plus this 0, 0, plus 0.3 minus 0.4 the whole square. This is Euclidean distance. Manhattan distance, simply take the absolute difference, isn't it? 0.25 minus 0.15 minus absolute this. Cosine distance, which takes the dot product of these two record, how the calculation goes on. In fact, whatever I have demonstrated, the built-in function which uses the cosine similarities. Your cosine distance is equivalent to 1 minus cosine similarity. That's the formula. So how cosine similarity is being calculated? It's a dot product, product 1, product 4, divided by norm of product 1, norm of product 2. So if at all, if you wanted to compute for this, guys, product 1 and product 4, the cosine similarity. Once you calculate cosine similarity, you can calculate the distance. So the numerator, how the substitution will go on the numerator side. See, sometimes these distance calculations maybe indirectly will be helpful for you when you do some kind of a data preparations and stuff like that. Maybe directly may not be, you don't involve in day-to-day large language models, but just take it as an additional piece of information. Somewhere around some part of applications, you may use it. So in the numerator, exactly, you're right. Term frequency is calculated for each document, whereas IDF, which is calculated across all the documents. Exactly. Uh, 0.15 into 0.25 plus 0.21 into 0.2 plus 0 into 0 plus 0 into 0 plus 0.3 into 0.4. Okay, that's the numerator. What's the denominator? Root of 0.15 square plus 0.21 square plus 0 square plus 0 square plus 0.3 square into root of 0.25 square plus 0.2 square plus 0 square plus 0 square plus 0.4 square. So mathematically, this is the formula. Okay, don't worry about this. Logically, try to understand. See, in multidimensional feature plane, okay, you can treat it like each column is something like a feature, isn't it? Like a feature. In a multidimensional feature plane, okay, the idea is something. If the two vectors are same, imagine if the two features, the two products are exactly same. When the two products are exactly same, let us assume that the data points almost align. Okay, the data points are almost aligned. In a two-dimensional representation, of course, we can say like one point. There is another point, almost with a different color. Let me show you. Let us assume almost aligned. When you try to see this like a vector, okay, this data point and this data point, okay, almost they are aligned it. The angle is almost zero. Okay, almost zero. Imagine there are two vectors I mapped from the origin like this. So this is the origin. So the two vectors are exactly aligned like this. How much angle they make? 0 degree. What is cos 0? 1, right? Cos of 0 degree. How much degree they maintain? They are exactly aligned, means exactly same feature, means cos of 0 degree is 1. That means your similarity is 100%. Okay. When they are orthogonal, means they are completely opposite. Okay, completely orthogonal to each other. They maintain 90 degree. Cos 90, cos 0 is 1, but cos 90 is 0, right? They're completely orthogonal to each other. 0. In the opposite direction, -1. Okay, this is cos 0 is 1. Sorry, cos 90 is 1. Cos 0 is 1. Okay, 0 and -1. So this is a logical way you can understand cosine similarity. It uses the cosine similarity score. Once you know the cosine similarity score, obviously what you can understand, the distance. If the two vectors are making 0 degree, obviously cos of 0, which is equivalent to 1, your cosine similarity score is 100%, which implies what is the distance between the two vectors? If the two document which has exactly the same content, cosine similarity is 1 minus, sorry, cosine distance is 1 minus cosine similarity. This is equal to 1 minus 1, which is equal to 0. The distance between the two vectors is 0. So that is the logic of cosine similarity. Are you clear? Try to understand the logical perspective, that is enough. Still, if you are interested in the mathematics, the formula is like, the general formula is like this: dot product of two vectors, a dot b, norm of a vector into norm of b vector. So this is a mathematical formula for cosine distance between a vector and b vector. Once you calculate, this is what cosine similarity. Once you calculate cosine similarity, your cosine distance is equal to 1 minus cosine similarity. So high similar vector will have shorter distance, right? The two documents are completely contrast. Okay, one is a sports news, another is a it's a sports news, another is a like entertainment, or sorry, a movie. It's about the movie, this is about the sports. Completely different content, contrasting content. The cosine similarity score will be very high, like 0.9. Sorry, very small, 0.1. And what is the cosine distance? Distance will be large, because 1 minus 0.1, we get 0.9. So the two closer document, your cosine similarity score will be very higher. Obviously, your cosine distance score will be smaller. That's the logic. So both are inversely proportional. Cosine similarity is inversely proportional to the cosine distance. So we use that logic to identify which record is similar to the remaining record. Okay, the application, you don't let us not waste too much time on this. Okay, because we will be deviating. Just you try to understand the data preparation part. Here our focus is on, for different application, how we prepare the data. That is the focus. I load these data and display the first 5 records. You can see the brief description, but however, if you wanted to see the detailed description, what you can see, DS, can see the detailed description about the first product, active classic boxes. description. So obviously your TF-IDF vectorization will do the data cleaning process and it's going to get the clean tokens. Okay, how this guy is doing, when you define TF-IDF vectorizer, you have an option here. You can specify whether you want to do the sentence tokenization or the word tokenization. You have two keywords, word or sentence, you can specify. Of course, I wanted to get the word tokenization, word. And whether you wanted to apply English stop word filtering, yes. So the moment you specify English, it will do the English stop word filtering. Another argument we use n-gram range. So typically we use unigram and bigram. Certain tokens you wanted to comprehend using a bigram like a t-shirt. Okay, I don't want to keep this T as a separate token, shirt as a separate token. I wanted to keep it as a t-shirt, it's a bigram. So when you say n-gram range 1,3, it is going to take unigram as well as the bigram. 1 and 2, 3 is not inclusive. Another argument I use, generally I don't recommend to use this, where always, in case if you are using this, better to leave it as a 0. This is something like, again, it's like a fine grained selection of the tokens. I don't want to do any kind of fine grained selection. Let me wanted to keep the everything as it is. Okay, what this is going to do, for example, if you set minimum difference equal to 0.01, means you are setting 1%. What you're saying, ignore the terms that appears in less than 1% of the documents. I don't want to do that. Maybe for certain application, maybe that process may be important, but here I don't want to use it because that is the strength of TF-IDF vectorization, isn't it? If a particular token which is going to appear less than 1%, that will be weighted more, obviously. So with the meaning, you should use it. Blindly, if you try to use such packages, very sophisticated packages, okay, you may end up with the wrong data preparation. You have to be very cautious. So any new API or library, when you are going to use it, try to understand the complete documentation page and try to understand each and every attributes. You should use it in a logical sense, whether this parameter which is going to be helpful for my application or not. You have to think and use it. Just because that variable is available or that argument is available, just like that, we should not use it. So hope you understood the meaning of this. Always set it 0. Okay, particularly when you wanted to do the sum for recommendation system, because the content based recommendation system, certain tokens are going to be weighted very high. I don't want to lose it. Even I wanted to keep those tokens, even if it appears out of 500 records, even if it appears for 2 records, okay for me. Because for 2 records, it is log base 2 2 divided by 500. That weighting factor will be calculated for that token. So once you have prepared this, okay, this matrix, once you have prepared, so how this is going to be implemented? Once you created an instance for it, okay, you have to do fit transform, just like your standard scalar and all, right? That's the way we. So which column? On the description column. We have 500 records. See, it's a very highly sparse matrix. Don't try to display this. Okay, even if you try to display this, it is going to say it's a very high sparse matrix. It cannot be displayed. Look at the column size. Can you tell me what is the vocabulary size from the shape of the matrix? What is the vocabulary? You can answer in the chat box. It is 52,262. 52,262. Put together all 500 records. Look at the size of the vocabulary. It's very huge. Almost half a lakh token. So it won't display, it will show you it is a sparse matrix. It's a sparse matrix. You can do certain calculation from the sparse matrix, but you cannot visualize it. Yeah, very good. 552K unique words. So calculations are permitted, mathematical calculations are permitted. So I'm going to use a mathematical calculation. So we talked about cosine similarity, right? So what function in Python is going to do that cosine similarity calculation is linear kernel. So I have imported this linear kernel from sklearn metrics. So it's a pairwise calculation. So whenever you wanted to calculate this, your matrix you have to duplicate and present, because it is going to work. Keep this matrix and keep this matrix like this. Okay, this is 500 cross 52k, 500 cross 52k. So how this linear kernel is going to work? It is going to take the first record, okay, first record, and it's going to calculate the cosine similarity score 1 to 500, and it's going to place it like this. First row, okay, first row, first record to first record. What is the cosine similarity score? Is it 100%? Because it is a self similarity, right? Document 1, how much matches with the same document? Obviously 100%. So your diagonal will be 1. You're going to get a diagonal is 1. So what is the similarity score for the product document 1 to the product 2, product 1 to product 3, product 1 to product 4, and so on? It goes up to product 500, product 1 to product 500. So how do you interpret the first row of the cosine similarity matrix? The first row of the cosine similarity matrix is the similarity score product 1 to product 500. Similarly, how do you interpret the second row? Similarity score product 2 versus, okay, P1 to P500. Third row, product 3 versus P1 to P500. Versus means P3 to P1, P3 to P2, P3 to P3. So P3 to P3 will be diagonal, P3 to P3 will be the self similarity. So 1. So either you can consider upper diagonal or lower diagonal, you can interpret just like a correlation matrix you are going to get. So what will be the size of this matrix? This will be 500 cross 500. Obviously, this is relatively a smaller matrix. You can visualize this. So once you have this numerical representation, whatever the task you wanted to do, you can do. This could be a recommendation system, or it could be like even you can build a ML model because you have a numerical representation, isn't it? You have a numerical. Even you can do the clustering. You can do some clustering, k-means clustering. Based on the similarity of the content, you can cluster the record. Men's wear, women's wear, kids wear, and so on. Once you have a numerical representation, okay, you can do anything according to the requirement. See, this is your 500 cross 500. This is the first row. It does not show the entire values. You could see the first record, first value, second value, third value, dot, 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 and last 3 value. Similarly, row wise, it's the unitless. It is a normalized range 0 to 1. Okay. So your cosine distance, it's a normalized range 0 to 1. Let us try to interpret the first row. Okay, even though what is the first row? How do you access the first row? Square bracket 0. If I access the first row alone, how you can interpret what is the first score? Product 1 similar to product 1, 100% similarity. What is the similarity score of product 1 with respect to product 1 with respect to product 3, and so on till the last score, the 500th score is product 1 similarity score to product 500. Okay, so what I do, I just do the arc shot for the 0th product itself. Okay. By default, what arc sort will do, it is going to sort these values based on the index, not on the values. That's what your arc sort will do. By default, it is going to arrange in ascending order, isn't it? Ascending order. That's why, look at this. We know it very well. 0th index, it's a 100% match, isn't it? Which guy is at the 0th index? Who's at the 0th index? Product 1. So the highest similarity score is 1, 100%. That is being placed at the last entry, isn't it? After doing the arc chart. Now the task is very simple. I can simply say, okay, recommend the top 5 product for my input product. Assume that a customer is surfing the first product. Active classic boxer, isn't it? We have seen in the head of the data. I just do the arc shot. I display the top 5 records, excluding this. Okay, excluding the self-similar record. The same product I don't want to recommend, right? Other than the same product, I am viewing a description of active classic boxer. Show me the top 5 records, which is similar features, similar attributes, similar tokens. So starting from, has to show 18, 493, 17, 171, right? 18, 493, 17, 171, 441. These were the top 5 recommendations. Okay, are you curious to know about what is there at 18th index? Let us see what is there at 18th index. Cap 1 boxer briefs, similar characteristics. Okay, what is your customer is surfing currently? Your customer is currently surfing that the description about this active classic boxer. The first closest product similar to this. The customer who has viewed this product also viewed this product, similar product. Let us see the next product, 493. 493. Again, that is also another active boxer brief. Okay, now let us consider a different record. Some random index. Let me choose a random index. Any random index? Please enter a random index. We can check the top 5 recommendation for a random. Which one shall I take? Okay, 342. 342. The top 5 recommendations. First of all, let us see what is there in 340. 342. Okay, it is a rock guide pants. So I think it looks like a mountaineering gear, isn't it? Mountaineering gear. So it's a nylon stretch woven pockets, multi pockets, easy to roll up cuff and stuff. That's how it's being described. And I wanted to see the which is a product very similar to that is rock guide shorts, similar characteristics. That is also climbing specific. The second closest is 212. The top 5 recommendations, rock guide pants again, then 213, rock guide shorts again. Then we'll see 352, simple guide pants. That is also rock climbing gear. 216, simple guide pants. So it's a meaningful recommendation, right? We did a very simple data preparation and how powerful application you can build. And instead of doing the whole stuff manually, okay, I just make it like a you can create an interface. So it's a piece of coding. You can write it. Even if you say ChatGPT, you give a specification. ChatGPT is going to give an interface, and you can plug in that interface and you can access it. So logic. See, nowadays we have a very sophisticated gadgets, AI tools are available. You should know how to make use of it. Nobody wants you to write the code from the scratch. Okay, that becomes, see, now your ChatGPT becomes a very sophisticated one day we used a calculator, right? Then we migrated to computer now. That people started working with spreadsheets. Likewise, the technology evolves. Okay, it's become inevitable. Like you have to use it to save your time. So you invest your time on the critical thinking rather than mundane tasks where you spend so much time on the regular stuff, on like strategical brainstorming, coming with a new idea. There you invest more time. So thereby you can increase your productivity. So what I have done, I have implemented a simple ML algorithm for it, nearest neighbor algorithm. You maybe hear about it. So I pass this matrix. Okay. Uh, you can cross check your K nearest neighbor is going to give the recommendations for a particular product. Let us see for 342. 342. 114, 212, 213. Okay, including that record also. If you can exclude it, okay, while printing it, you can exclude that. You can do it like this, 1 colon onwards. So this is self similarity record, which is the next closest index, 114, right? What we have seen. Second closest is 212, 212. Third closest is 213, then 352, finally 216. So the same answer we have got. So whichever the record you wanted to check, you can pass that record index alone. It's going to return the top 5 recommendations, including the cell. So these are the active classic boxes, what we have checked earlier, followed by rock climbing guide bands we have the second example.